Hi, I'm Tommy, and I'm a professional paleontologist. By day, I use the latest data science techniques to reconstruct ecological and evolutionary changes from the fossil record. But by night, I investigate cryptids, the paranormal, mediumship, the occult, politics, history, philosophy, and even God himself. You know, all the things that good little scientists are supposed to avoid. If you want to join me on my journey, friend, be so kind as to like and subscribe. And welcome to Creepy Puppets Presents. Hey folks, so I like to periodically update you with things from my research, interesting things I've worked on, either directly tied to my dissertation or related to that I thought was neat. So if you'll just give me a moment to remove my picture-in-picture, we'll briefly discuss this project I worked on in paleovolcanism, or the impacts of volcanoes on ecology as observed through the fossil record. My little talk today is called Fingerprints of Fire, Developing a Method for Computationally Identifying the Impacts of Explosive Volcanic Eruptions from the Fossil Record. So this studying of ecological impacts of volcanoes from a fossil record is a bit of an open problem in paleoecology, and I thought, well, let me take a crack at it. So first, I need to explain what an explosive eruption is. An explosive eruption is the ash, pyroclastic flow, big column of ash, ash fall, acid rain kind of eruption, whereas an effusive eruption is the bubbly lava kind of eruption. So when this happens, obviously there's a range that's hit with the pyroclastic flow and everything dies. But there's also soil acidification and soil hydration from ash interfering with groundwater absorption that radiates outward for miles, and these impacts can last for decades. And there has been some evidence that these eruptions disturbances have been documented in the fossil record. So, usually though, the way paleontologists look for evidence of volcanism is to look for fossil tephra. Tephra is just a fancy word for ash, volcanic ash. So the idea is we should be able to find evidence of volcanism and through its ecological disturbance alone. And so the idea is that, well, we should be able to predict what kind of pattern, because we know what ecological disturbances occur, we know what pattern should occur in the data, so we can, try to look through the data and see if we can find it. But, first we have to identify what that pattern would be. And so I thought of sort of two approaches. One would be sort of idealized perfect data, and the other is, what it's likely to look like statistically from the fossil record. And so this is what our data actually looks like, just plotted out. So you can see percent abundance of pine by pollen grains. So, sometimes it's 0%, sometimes it's 10%. It's discontinuous and jagged, and it's kind of wave-like. So now, just sort of returning to the ideal case for a moment, if we imagine that acidophilic species that like acid, are going to be more likely closer into the volcano where we expect soil acidification to be greater. However, we expect that there to be a certain radius from the volcano, what I'm calling a critical radius, in which everything should be dead, accounting for being hit with pyroclastic flows. So, obviously, syneruptively, so at the time of eruption, and because we're talking about geological timescales here, we're mostly dealing with, within a year or two of the eruption, we expect that everything in the critical radius dies, but that acidophilic species will increase proportional to the distance away from the volcano. So actually an inverse proportionality, more acid tolerant species the closer you get to the volcano. And so taking a look at the algebra of proportionality, we can quickly derive this equation where the percent abundance of an acidophilic species at a radius greater than the critical radius around the time of eruption can be described by k sub rho, radius raised to the negative rho, where these are experimentally determined constants. And so this is kind of what it looks like. Nothing here, then a line of discontinuity where our equation doesn't describe it, and then acidophilic species, much more common in here, going out. So that's great for syneruptive conditions. How do we think that this system will evolve over time? So one intuition I had is if you're close into the volcano, your impacts are going to be felt more immediately, and they're going to be bigger, and they're going to last longer, and all of those things are going to decrease as you move away from the volcano over time. So this is close in on time. So notice that this kind of looks like a sine wave, and this is certainly wave-like. So my intuition was, okay, this is the generic form for a sine wave. Maybe we can approximate these close-in conditions using a sine wave. So taking our intuitions from the previous slide and chugging through the algebra of proportionality, we end up with this equation. Now, I ended up using a Python script to do a simulation of equation 2 using arbitrarily generated constants. And so this is sort of syneruptively, and you see, it's not too bad a description. But as time goes on, it becomes less and less useful of a description. So, maybe approximating sines isn't good, but I still think that there's some validity to this intuition. And we'll talk about that in a second. So one thing that I thought, my next intuitive thought is that, so close into the eruption, if impacts follow soil acidification, and soil acidification follows the ash cloud, then it stands to reason that we could describe this with a diffusion equation, because the dust in the ash cloud moves by diffusion. We know this from prior work, including work done by Dork Sahagian here at Lehigh. We also know that soil acidity is in some way removed by diffusion, and also we know that organisms from outside of the blast radius will diffuse their way back in to the area. And so we think, well, diffusion might actually be a really good model. So if you're not familiar, you model diffusion with the heat equation, where the change in concentration over time is an experimentally determined diffusivity constant times the second derivative of the distribution in space, the initial distribution in space. So if equation 1 represents that initial distribution, then we take its second partial derivative with respect to radius, which, as it happens, was the only variable, so there's no difference between that partial and the regular derivative. Then we take the partial integral with respect to time, and we get this equation. And when I take this equation and toss it into my Python sim, this is what I get. So this is our initial concentration again, and you can see it flattens out farthest out. There's still some impacts close in, and there's the greatest impact here. But as time progresses, that impact flattens out over time, and that's pretty much exactly what we expected. And also, we stipulated that this equation was only an accurate description outside of the critical radius, so we can sort of ignore this part here. So that's great. We have a mathematical framework to describe idealized data, but our data is probably not going to be that flawless. So we want to think, how can we measure our data statistically to be able to understand what's going on? And when we come back to this intuition, I want to go back to the idea that max values should be inversely correlated with distance from the volcano. So that's a simple measure we can take. So it seemed reasonable to me that I can run that correlation, and I can also do mean and I can also do mean and standard deviation while I was there. So I decided to study the Vesuvius eruption, which occurred in 79 AD, and I was going to study this using fossil pollen that I had queried from the Neotoma Paleoecological database. Now, normally I would do this with an API that allows me to analyze lots of data, but the API is down at this time, so I was limited in the amount of data I could look at. So I looked at 3 sites and 4 taxa, which I'm going to describe in a later slide. So here are our sites. This is Mount Vesuvius down here. This is Lago di Martignano, just outside Rome, Lago della Sessa, central Tuscany, and Lago Padule in northern Tuscany. And they're all approximately equidistant from each other and the Vesuvius. So here are our taxa. Pinus, pine trees, these are acidophiles. They love acid. We expect them to be much closer toward the volcano. These are Quercus. They're acid tolerant. Um, Grasses, early successors, acid tolerant, we expect these to be much more common near the volcano. And juniper, we know that juniper is very negatively impacted by the presence of volcanic ash. So we expect to find this more common far away from the volcano. So I was holding juniper out for validation purposes and just looking at these three. And of course, I struck out, but especially with this column, because that's the one I thought would be the important column. So, that hypothesis didn't work. And here's why I think it didn't work. Um, you know, this is the age depth correlation. So that is ideally for every 1 centimeter you go down, you expect, the same amount of time to be here. And so the closer this graph is to a straight line, the better. But this is really not close to a straight line. So that means that our measurement of time is kind of messy. And if you look at the jagged graph, you can see like at some points there was a 600-year gap between data measurements. But the most important thing to look at here is this blue line, and you can ignore that. That's a point of discontinuity. So this is 1 over the sedimentation rate. So years represented by each centimeter. And so where we would be looking for evidence of volcanic eruption is right in here-ish. And so what you would find out is, wow, this is maybe 70 years per centimeter. That's just on the very edge of what we would expect to be the resolution of the impact. So we're not getting resolute enough data to be able to really see the impacts of these volcanoes. So I had a second thought, right? Maybe over the course of geological time, volcanoes give a statistical advantage to taxa that are closer to volcano or disadvantage to certain taxa. And so all I did was I took the percent abundance of each taxa and over the whole record and just ran a simple pairwise Pearson correlation test in R from distance from the volcano, right? And I did that. I got some really interesting results. So there's nothing of note going on with Quercus, but Pinus is statistically significant, and the negative sign means that you're more likely to find it closer into the volcano. And as impressive as that is, Pokei is really quite powerful and, much, much more likely to be found into the volcano. So that is exactly what we expected. And this is what that graph looks like. But when I run it with Juniperus, while I find a statistically significant correlation, it is also negative, and we would expect that number to be positive. In other words, you're more likely to be finding juniper far from the volcano. So what's going on here? Well, it's possible that there are other ecological factors that are affecting these distributions aside from the volcano. Maybe fire, maybe, pine is really small. Maybe it's not ecologically significant at all. Also not for nothing, but I'm going to go back to this graph. It appears that Lago di Martignano, which had the highest percentage of grass, appears to be located in some kind of plain. So the point is that there may be other ecological phenomena going on that can account for that. Our first hypothesis struck out. Our second hypothesis is a maybe. The Juniperus does kind of argue against it, but the other two argue for it. But ultimately, more data is going to be needed, both from Italy and from other volcanoes, to know for sure. And whatever the result, we have the beginnings of a mathematical model to study vegetation impacts. And we've clearly observed the statistically significant distribution of functional traits, so acidophiles, early successors, through space in Italy. So that is still an interesting observation, regardless of the cause, and it's something that I'm interested in doing more research on in the future. So this would be the point where I would give Q&A, but since this is a recorded video, you can't. So if you have a question, feel free to leave it in the comments. Give me a second to get back my picture-in-picture. And so that's been some cool research I have been up to lately. Thank you for listening, and I'll probably be doing one of these videos at least once a semester. So thank you, and Thank you and take care, folks.